Welcome, my name is Michael, and I would like to present you a Kinetic of ion molecular interaction simulator, KIMI. This application was built as a part of my PhD studies and is freely available for everyone who needs it to simulate ion chemistry. In this video tutorial, I would like to introduce this application, describe its purpose, and demonstrate its use. KIMI is a Windows-based application that allows you to simply draft a set of ion molecular reactions into a graphical interface. The set of reactions is then automatically transferred into a set of differential equations and numerically solved using the classical Runge-Kutta algorithm. The simulator was built to support experimental results from soft chemical ionization techniques, but can be also used to simulate other problems related to ion chemistry. First, let's quickly describe what is soft chemical ionization. The soft chemical ionization mass spectrometry, SCIMS, is a group of analytical techniques using chemical ionization for rapid detection of organic molecules in gases. It includes selected ion flow tube mass spectrometry, SIFT-MS, proton transfer reaction mass spectrometry, PTR-MS, selected ion flow drift tube mass spectrometry, SIFT-DT-MS, and also ion mobility spectrometry, IMS. These techniques are widely used for analysis of breath, environmental analysis, or in homeland security, as they can quantitatively detect trace levels of various organic molecules in real time. The power of each of these instruments relies on ions rapidly reacting with other molecules. If the ion chemistry of these ions is understood, the instruments can be easily used. However, the ion chemistry can be also very complex. For such situations, it is useful to simulate if the proposed ion chemistry agrees with the experimental observations. And that's why we built KIMI. As I will demonstrate later, KIMI allows you to draft complex set of ion molecular reactions using a graphical interface. Set of reactions will be then transferred into a set of differential equations and solved by classical Runge-Kutta numerical approach. Results are then shown in a graph from where can be downloaded or compared with experimental results. Here I am showing two illustrative examples of such simulation. The first one is a simulation of clustering of hydronium ion H3O+. The hydronium and SIFT-MS react with neutral water molecules in a helium carrier gas in a reaction sequence forming higher water clusters. Using KIMI, I was able to simulate the ion distribution for different concentrations of water molecules and reconstruct the observed experimental results. In the next one, I simulated similar but more complex problem, where we also injected acetone vapors into the system. As we can see, the reaction schema is more complex than the previous one. However, we were still able to simulate the experimental results. Before I start with the demonstration, I would like to acknowledge the founder of the project, the European International Training Network Program, IMPACT. Let's get started. After we open the application, in the center, we can see the reaction grid, where we will draw our reactions, and on the right side some other reaction options. Before we start drafting our set of reactions, we first need to define reaction particles that we will use in the simulation. To do that, we have to go to Properties and choose Resource Manager. Here we can create and manage our ions and neutrals. Let's create a simple simulation where hydronium ion will react with water molecules and acetone vapors in a flow tube with helium carrier gas. To do so, we have to create our first particle, hydronium, by writing its name and formula H3O+. The short name is a name that will be presented in the reaction grid. Let's choose H3O+. Next, we have to define some properties of our new ion. First is the reduced ion mobility. The value of reduced ion mobility need to be specified if we want to simulate ion reactions in the drift tube, for example in PTR-MS or IMS experiments. otherwise it will not be used. As we may know, reduced mobility is a parameter depending on the electric field. This dependence can be described by a simple function of E over n parameter. To create this function, we have to click on the button and select the function that best represents the reduced ion mobility for selected ion. For hydronium, it's a simple task, as the reduced ion mobility for different E over n can be found in papers. Here I am following the Ellis paper from 1978, where we can find hydronium ion mobilities for several E over n values. For hydronium, the reduced mobility at low E over n is around 21.5, and then falling down to 16 for E over n 100,000. We can quickly reconstruct this dependence by selecting a linear function. And the first parameter a can be 21.5, and the second parameter b can be minus 0.05. So we achieved around 21 at low E over n and around 16 for E over n 100,000. Clicking OK, we save the mobility function. The next parameter is the initial number density at the beginning of the simulation. As hydronium is our reagent ion, this value is not 0. Let's say we start with 1 million particles in cubic centimeter. The last parameter we need to define is diffusion coefficient or diffusion constant. This can be again found in literature or obtained from quantum chemical calculations. However, for reactions in helium, the diffusion constant can be easily estimated following the publication of Spaniel and Driahina. Here they found a parametric function fitting the diffusion constant of ions in helium. The ion diffusion is parameterized by ion mass, as is shown in this graph. Thus, knowing the ion mass, we can roughly determine the diffusion coefficient of ions in helium. If we press Estimate Diffusion Coefficient button, the diffusion will be estimated from the ion mass based on this parametric function. Clicking at Add, we have added hydronium into our particle list. Next ion we have to create is hydronium water cluster that will be formed by a reaction of hydronium with water vapors. Again, we need to specify the name, the formula H5O2 plus, and for the short name we can just add W here. Again, the ion mobility of this cluster can be found in the publication of Ellis, which is around 17.3 for low E over n. And then falling down to around 14 at E over n 60,000, which is correct. Okay. Hydronium water cluster is a product, thus its initial number density is 0, and again we can just estimate the value of ion diffusion coefficient, and clicking Add, we add this ion as well. The last ion we will use in this simulation is a production of proton transfer reaction between hydronium and acetone, the protonated acetone. Formula of acetone is C2H6O, but because it's protonated we need to add one more hydrogen. And for short name, we can just select CH+. For its ion mobility, I don't know the precise value. I will just estimate it's just a little bit lower than the ion mobility for hydronium cluster. I will just use 15 here. Of course, if I want to do a proper simulation, I will need to find the exact value of the ion mobility. I will click OK. The number density of protonated acetone will be 0 as it's a product, and last we have to estimate again the diffusion coefficient. After we specified all three ions we want to use in the simulation, we have to specify also the neutrals. Our first neutrals is helium. This is our carrier gas and it will be part of our reactions. So we have to add its name, the formula, and the short name. We will select that helium is a neutral, and the neutrals don't have specified ion mobility nor diffusion constant here. The number density can be just estimated at this point, let's say power of 16, and we will modify this value later when we will know the pressure in the flow tube. The next neutral we will use its water vapors with formula H2O and short name just a W. The number density of water will be lower, so around power of 13. Clicking add, and the last neutral we will use is acetone with formula of say C3H6O and a short name AC. Acetone can be at trace levels, thus the initial number density will be around 1 million. Okay, as we have all particles we want to use in our simulation, we can save them by pressing OK, and the particle list can be accessed again or modified anytime in the future in the resource manager. The list can be also saved into a text file and loaded later. Now we can create our first reactions by placing the ions into the reaction grid. As we'll deal with ion chemistry, we will be placing ions, and those are our main particles. So first will be hydronium, this is our reagent ion. The second will be hydronium water cluster, and the last can be a protonated acetone. The reactions will be made by dragging the mouse between ions, and when the connection is displayed we can modify the parameters of the reaction. For the first reaction, formation of hydronium water cluster, H3O+ is our main reactant and H3O plus W is our main product. But we also need to add neutrals into the reaction. The first neutral we have to add to the reactant side is water and helium, because this is a clustering, and clustering is a three-body reaction. For products we need to add only helium, as water reacts into the water cluster, the hydronium water cluster. Then we can specify the direction of the reaction, and last we have to specify the rate constant. The rate constant, similar as in the case of ion mobility, can be a function of electric field. For flow tube simulation we can use a constant value, but for a drift tube simulation we need to choose a proper function. For this tutorial let's just select the constant value. It's important to note that this is a third order reaction, and thus we have to add the rate constant in an appropriate dimension, which is centimeter on power of 6 per second. For this reaction the rate is around 7 to the power of minus 28. Clicking OK. And now we can apply our parameters and the reaction has been formed. We have to do the same for the reaction of hydronium with acetone. Again, just by selecting hydronium and dragging mouse from it over a protonated acetone and selecting neutrals for the reaction. For this one, the hydronium reacts with acetone, forming protonated acetone and neutral water molecule. Again, we have to specify the rate constant, and for this reaction let's again take just a constant value of 3 power of minus 9. Okay, and applying, we have created our second reaction. All the reactions we have created will be remembered, so in the future you don't have to specify all of these parameters again, but you can just select them from the list. For example, if I delete this ion and I will add it again, I will just select the reaction from the list. Now, as we have created reactions, we have to specify the physical properties of the simulation. We can do that in properties and calculation properties. In this window on the left side are the main physical properties that are used in the calculation, and on the right side are supporting calculations. First, we have to specify our carrier gas if we have one. This information is required for specific type of reaction rate constants operating with a collisional energy. And this simulation we are using helium. Next, we have to specify the pressure inside the flow tube, for example 2 millibars, and then we have to specify the temperature, which can be 310 kelvins. The next crucial parameter is the ion flow velocity. This is the ion flow velocity at zero electric field. If you know the value, you can add it into this box. For drift tube simulation, this value is usually not important, as the flow velocity is much lower than the drift induced velocity. But for flow tube experiments, this value is important, and in that case we can estimate the ion flow velocity from a neutral gas, ion velocity, and the other flow tube properties. For that we can use our simple calculations on the right side. Here we can add values of the carrier gas and sample gas flow rates that are flowing into our flow tube. And using these values and other dimensional parameters, as is tube radius and the drift tube length, the software will estimate the carrier gas flow velocity, from where, in our case, if it's a laminar flow, the ion flow velocity can be estimated. So let's update the radius of the cylinder to be 0.5 centimeter and the distance and the length, tube length, to be 4.5 centimeters. Now we can take this value and copy it over, and now the software will give us estimation of the ion flow velocity, which we can use here. Is it also important to note that if the flow tube radius is too small, the pressure loss will be created along the reaction tube. This pressure loss is calculated here in this box and can be accounted for. Additional important parameter in the supporting calculation is the carrier gas number density, which is shown here, calculated from the pressure and the temperature of the gas. This is the correct value of the helium carrier gas number density that we have to use in our simulation. To continue, last parameters we have to specify are the dimensional parameters, the flow or the drift tube radius and the tube length, as we just did a second ago, and from the flow tube length and the ion flow velocity, the drift time, the total drift time, will be calculated, and vice versa. So if we know the drift time, the software will adjust the ion velocity. In the calculation properties window here, we are selecting if we wish to solve our differential reactions according to the time or a space coordinate. Usually we are selecting the time coordinate as we want to use a time differential, but for example for a drift tube situations, the calculation has to automatically switch into a space coordinate. The last parameter we have to specify is the number of calculation steps. This defines how small will be the differential for the numerical calculation. The size of the differential can be seen here. For large values, the calculation will be more smooth, but of course it will take more time to be executed. Also for very small values, if the concentration of particles change significantly, the calculation may not run properly. Therefore, it's important to find an optimal number here, considering the calculation time and the quality of results. I recommend not to choose values below 100 and over 2000 for the system of this type. The last option is to disable or to enable the diffusion losses. After clicking OK, the values will be saved and we can proceed into the calculation. On the next window, we have our recapitulation of our reactions and rate constants, and also all particles with their initial concentration. We can also modify them here if we want so. For example, we can adjust the helium concentration, as we just saw here in the properties. So we can again have a look. 4.67. Alright. Pressing the apply button down here, the program will take all the initial values, convert the reactions into differential equations, and solve them along the coordinates. The results can be seen graphed here, and switching into the data plot, we can manage them. For example, we may not be interested in the neutrals, but only the ions. Also, we can show the data in the linear or logarithmic scale, or change the type of the x-axis from the time into a distance. So as we can see, we have calculated the distribution of ion concentration along the flow tube, and the data can be exported by clicking on this option. Now we can play with the simulation by adjusting the initial values. For example, we can change the rate constant to be much higher or much lower, and we can run the simulation again. If we are not interested in absolute values, but rather we want to see relative values, we have this column of numbers here. Using this, we can specify the groups of particles that we want to use for a calculation of relative concentration. For example, we want to calculate relative concentration of only ions. We will choose different group for the ions, and clicking on the box, the program recalculates the values into a relative based on the group selection. So far we have done a simple simulation along the drift tube. Next we can set up a simulation for changing concentration of one particle. For example, we want to know how is the ion distribution changing for various concentration of neutral water vapors in the system. For that, we will allow the dynamic concentration change, and we will select one particle, the water in this case. The initial concentration value is our previously specified initial value concentration, and for the final value we can add, for example, 15 here, and we can run the simulation in 100 steps. Now the program will calculate the ion distribution along the tube for 100 different water concentration in a selected range. Each selected water concentration from the interval will be used as a new initial concentration, and the program will run the simulation with these settings. After the simulation is done, we can see how the water concentration affects the ion chemistry. Also, we can still overview the data at different position or the concentration profile in the tube for every water concentration. Okay, I did not mention before that you can also see the data as a mass spectrum. Finally, we can introduce the electric field into our simulation. Again, we will allow the presence of electric field, and then we have to specify if we want to use only a constant value of E over n, or we wish to investigate the ion distribution for a range of E over n. If we select the dynamic change of E over n, we have to specify the initial and the final value, as well as the amount of steps between them. The program will now run the simulation for each of these E over n values. You can also combine the dynamic change of electric field with the change of the concentration. If we run the simulation now, we can see that it takes more time as the program simulates the tube profiles for 11 E over n values as well as for 100 water concentration. Alright, after the simulation has finished, we can again inspect the data. For example, the E over n profiles for different water concentrations, or the concentration profile for different E over n values, and also the tube cross sections. After we found the results we are interested in, we can again just export the selected plot into the text file. All calculations that were executed on this window, reaction view, are saved in a calculation memory, and we can access them in the data management list. And here you can see our previous runs. If you want, you can inspect them and restore the settings that was used for this particular calculation. Alright, and in the last part I will show you how you can import experimental data into the simulation. To do that, you have to select the data management list and then load experimental data. After clicking on the button, the load window will appear, and here we have to select what type of experimental data we want to use. The first option is a universal data input. This will allow you to insert any type of data, where the first column represents the x-axis and the first line represents the header. For example, I have a data file here with some random numbers, and by selecting it, the header of each data column appear in the list. Again, we can import absolute values of this data set, or we can take relative numbers in a similar way we did before by specifying the particle groups and clicking on the relative data option here. Clicking OK, data are imported and we can compare them with the model. Universal data can be compared with any type of calculation in the program. So the universal input may contain E/n data, concentration dependence, or the mass spectrum. The remaining inputs are more specific, optimized for SIFT-MS Profile 3 and SIFT-DTMS multi-ion monitoring data, as we have those experiments in our laboratory. The SIFT multi-ion monitor data selection is optimized for measurement of water profiles, focusing on intensity distribution of reagent ions. The same goes for the SIFT-DTMS selection here. I have an example of such SIFT data where I was investigating the effect of neutral water vapors on acetone ion chemistry. By selecting the data, I have some additional options where I have to specify the type of the reagent ion. I use H3O+ in this one, and the data are then presented as a very specific function of reagent ion distribution that is dependent on the concentration of water vapors. The software will recognize this type of experimental data and it will adjust the simulation so it's comparable with them. Oh yes, for this type I have to specify what is the primary reagent ion and what is the secondary reagent ion. Yes, and I need much larger window here. Like this, for example. That way I can quickly reconstruct the experimental profile by adjusting the rate constants. So that was the last example I wanted to show you. I hope the tutorial was useful. If you find any problems with the KIMI or do you have any new idea, I'm always happy to update the software so it can be more useful. For now, thank you for your attention.